So historically, some predictability started to arise. So it's proposed that deterministic curves and predictability concepts in the 1960s. And this theory clearly says that the irrefutability of the predictability of weather in a non-adaptive system. So what it actually showcases that some physical systems, while not deterministic force, the prediction of the future will necessarily be perfect. So the most of the time, prediction of the predictability of weather in non-adaptive system. Across various fields also now. So when it comes to the most predictable system is the pendulum. You have a pendulum, this is the best example for a predictable system. So if two transitions starting close to together, some small error in the expectations can actually result in large variability. So what we comes to atmosphere in our system, and this system even though is slightly very small difference
तिथे आवाज केला
whatever
की
the
पण असं
metropolis
बॅकग्राऊंडला अजून आवाज येतो
can
त्याचा
cause actually
पण झाली
prediction that may be part from that.
असा आवाज येतो
So such systems has thousand instrumentation. That is what we call as variability. The person which can have some problem so that the result is predictability or adjust for weather, whatever else that is the indicators before of the different destinations using different forecasts. So seasonal forecasts, on the other hand, they try to use boundary conditions, and actually they are much more useful to get more information of how the atmosphere changes. So we know that the tropics essentially actually require the polar circulation, and they're very sensitive to the variations. So similarly, you can use the other fields like soil moisture, snow ice, and other things as well. Try to get these boundary conditions to drive our atmosphere. So therefore, the seasonal forecast also is possible. That is mostly coming from the activity of the second kind. So now, if you try to look at there are several features to measure the predictability. Actually, I don't want to read each and every one of them. So there are so many technical ways of estimating the predictability. But one important thing that we should have understand is that almost all these empirical predictability measures try to have one they assume that this is a distribution that tends to form. So that is one of the major challenges in using it. So, but if you are actually trying to estimate that using the model principles itself, then we try to what we do is that assume that model is perfect. That is the assumption that we have mentioned already. And each ensemble, you will try to correlate with other ensemble and try to get that what is the potential predictability. Potential scale and that is the predictability limit. So that is most frequently used across the all modeling centers, but they also use this different metrics, but this is most important. However, when you try to measure using this technique, it costs a lot of HPC resources, time, everything. So that's why people have come up with some of these empirical predictability measures that are actually useful when you don't have many of the resources. So, so if you look at any of these things, but in this my talk, what I try to follow most of the time is that predictability that is coming from the model itself. Okay, so there are several studies done within the IITM by looking at various other measures. When from the information theory also people have looked at how the predictability limits can be determined. But in my presentation, we try to focus on the potential predictability coming from the models directly. So this is the system climate dynamics of the Earth, planet Earth. You have solar radiation and different gases and albedo, all these things that are there. So when it comes to predicting the weather, only these bottom two are important. Sorry, I cannot see more. So it is at a wrong location. So these tables of shear, flows, stratification, and other things, they actually determine the weather. When it comes to external forces and weather combined to that, that gives you the climates. So this is how you should remember yourself when you look at climate or weather predictability. So here I'm showing you prediction skill versus predictability. So if you look at left, all these three panels are for different ensemble scale of northern hemisphere, land, monthly temperature. This is precipitation. This is the SST in the tropics, 3.4. So you can see that the scales are very weak for the northern hemisphere land temperature beyond 1 or 2 months. So whereas when it comes to SST, you can see that very clearly that you have the scales very much going up to 6 to 8 months. I think it is 8 months or 9 months, I don't know. So it goes up to at least 8 to 9 months, and then you should see that some drop in the scale. Then again, you see picking up. So this is what is called the spring predictability barrier or console. So if you look at the predictability of the same parameters, what you notice is that is always the predictability is higher. So this is estimated the method or whatever I mentioned before. So you can see that the predictability is much higher, whereas the prediction skill is much lower. So this is what is called
predictability gap or prediction gap. So that is true for all the almost all. So what is that? Clearly, we are trying to get a clarity on this. Is that tropical SST is much more predictable and it has a better predictability compared to other temperature or precipitation alone. Okay. So one more information is that predicting temperature is much more or slightly easier compared to the precipitation. Because precipitation is combination of many other processes, so getting that correctly is difficult. So these are the concepts you should keep it in your mind when we talk about other things. So actually, now we want to understand what controls the predictability of weather and climate. So first and foremost, initial conditions. The chaotic, sensitive nature of the atmosphere, that is what controls the predictability. And second most important component is the model imperfections. The dynamical model equations and parameter schemes that are there in that. So those imperfections also actually ensures that it also controls or minimizes the predictability. So boundary forces from the ocean, soil moisture, and sea ice, they also actually, if they are not represented proper in the model, then you don't get better predictability. So these are the most important components for controlling the predictability. So now let us come to monsoon variability. So you know that monsoon has different scales of variability within the system. So first one shows you 1941 how the rainfall changed. So that is the first part, and this is the MISO spectrum. And if you put observations and the MISO reconstructed values, then you can see that most of the rainfall is coming through that MISO oscillations. Then there is a decadal variability. So these are the different uh, scales of which are very active in the monsoon region. So you need to have a prediction systems for all these things, maybe differently, or a unified system, whatever system what. But at present at IITM, we are trying to use all different systems for making these forecasts. So just before starting this lecture, our guest was asking me, so what is the status, what is the prediction skill of the models in the Indian region? So there is a monsoon mission program that we have started 2012. So before that, we have actually tried to analyze how well or how good the predictions for different spatial and temporal as well. So if you look at short and medium range forecast, so by day 3, you don't have much of, beyond day 3, you don't have much skill. So if you look at the 5 days forecast, the whole of Indian region, you don't see any color. It's almost white. That means there is no skill. So that is the state of the art at that time before we started monsoon mission. That started in 2012. So then if you look at the extended range predictions, then what you see is that there used to be only empirical models, but you know that empirical models have its own limitations. They are pretty good when they are developed, but when actually they are operationalized, things will change significantly. So when it comes to seasonal prediction, so the empirical models skills looks very promising in particular decades, but in other decades it is not. So, but whereas if you look at the dynamical models, that is what is the PDF is shown here. So this is the PDF of correlation between observations and the model. So you see that that is very close to 0. So that means dynamical models don't have any skill in predicting monsoons. So that was the reality. But if you look at the predictability limit, that is each ensemble member to other ensemble member, this is what is the red curve. That shows very clearly that the skill is about close to 0.7. So this is the predictability limit of seasonal prediction. That didn't change for a very long time and it remained there for several decades or so. So whereas, so you can see that the predictability gap is very big, the prediction gap is very big, so 0 to 0.7. So that is how we started monsoon mission. Then we started progressing hence from there onwards. So what do you notice here again? The 500 Tabasco geopotential height. how the error grows in the models. This is again from the CFS version 2, Krishnamurthy's 2019 paper. You see that 1-day error, 5-day error, and 10-day error, and the forecast error using a empirical formulation. And you see that the errors goes very fast. You see that after 10 days or 15 days, the error is almost becomes stable. Similarly, if you look at the rainfall, the growth is much faster than geopotential height. And what you notice is that there's a faster growth of errors in the monsoon region compared to Pacific region. So this is the also you have to understand that when it comes to monsoon, it is not just ocean atmosphere interaction, the land and also sea, the ice from Himalayas and sea ice from Antarctica also plays a very important role. So therefore, it is much more complicated, and therefore the error grows much faster the monsoon region. So if you are trying to make forecasts of monsoon, there are different challenges are there. We all know that monsoon is majority of the monsoon is modulated by the ENSO. Okay, so ENSO can explain almost 40 to 50% of the internal variability of the monsoon internal variability. If you know the state of ENSO, then you can actually reconstruct monsoon by almost 50% accurately. But most importantly is that what happens is that this is the scale of the model, ENSO prediction scale over time in C5. That is the volume model that has handcast for a long period. So if you look at this starts sometime in 1950s and up to present. So there's a May starts and November starts. What you notice is that in November starts you have very good skill, whereas in the May you don't have much of skill in the models initially. But now that problem is resolved. Most of the models don't have that problem. So if you try to initialize your monsoon models or the dynamical models during this period, so there is a quite possibility that ENSO state may go wrong in the models itself. So therefore, predicting monsoon itself, and you try to initialize your models sometime in the spring and early summer, then what you notice is that variability that can be explained by models is very, very low in February, March, April, May. So it goes, February it is only 5%, 20%, 40% like that it goes. So when you try to initialize your models anytime during this period and try to get an idea about monsoon, how it actually evolves in the coming months, this is the biggest challenge in the models. So this is the one biggest challenge for making a seasonal forecast of monsoon in sometime in the spring itself. So the second challenge is that, as you have seen that the mid latitudes, if you the predictability beyond a month or so is very, very low because the signal is very, very low there. The seasonal signal is very low. So but within the tropics, if you look at it, both SST and rainfall, the variability, internal variability is also very, very low, particularly of the monsoon region. So this is low variability both in SST and rainfall in the Indian Ocean region and also over the monsoon region actually makes it very difficult to predict. If you look at the internal variability is only about 10% of the mean. So that 10% you have to predict the variations within that 10%. So that is the another challenge. So most importantly, there is we all know that ENSO and ISMR, as I mentioned before, it all explains almost 50% of the monsoon variability. So, but in the models, the relation is much, much stronger. The ENSO ISM are very, very strongly coupled to each other, whereas in observations, it is not. So only 50%, but whereas in models, it explains about 70 to 80% of the variability comes only from the ENSO itself in the models, dynamical models. So that we have looked at why that is happening, and we have noticed that the synaptic variability of the monsoon low pressure systems is not well captured, particularly in the month of August in the models. That's why it is not able to get that relation very well. So this actually has another impact on monsoon relation itself. the IOD, the Indian Ocean Dipole, and ISMR relation is also very, very weak in the models. So it actually is weaker in the model, in the observations itself, but in the model it is much, much weaker. So these are the challenges that actually limits the predictability or prediction of monsoons. So at IITM, we have started with a borrowed CFS version 2 model from NSEP, and we try to increase the resolution, urgent resolution of the atmospheric model. So that is what we call as a MMCFS version 1. But on this MMCFS version 1, that is Monsoon Mission Climate Forecast System version 1, on that lot of developmental activity happened within the institute, and we got a good idea about what process will actually try to improve monsoon simulation and also prediction as well. So in recently, about 2 years back, we have moved to a new system completely different from NSEP, and we have moved to now Monsoon Mission Climate Forecast System version 2. So details are given there. So a lot of work is going on in this direction to understand how the system will perform and what is the benefits we have obtained. I will show you shortly. So if you remember the predictability, what controls the predictability, what we have shown is that the mostly the errors that grows in the models. So there are the systematic biases in the models that we all know that. And if you look at this is the MSCP version 1 precipitation difference between version 1 and GPCP, you see that there is a strong dry bias over Indian land region. That bias is there, but in the new model, but it reduced significantly. That you can see the difference between MSCP version 2 and version 1. So if you look at the other, this is the same for real precipitation map. So these biases have started decreasing in the new model. And also SST, we used to have very cold SST in the Indian Ocean that now actually replaced by slightly warmer SSTs. So that is one good thing. And most importantly, the winds and the particularly 850 hectopascal winds have improved significantly, and we are surprised ourselves to see that the complete tropical circulation is very well captured by this model. So not only that, the wind shear is also improved. So therefore, once the wind shear is improves during the monsoon season, you also expect to get more or reasonable or realistic ISO as well. So that people are still trying to understand how it is going to improve. So another important is the telecasts also started improving in the new MMCS version 2. I will show you in the next slide what is that actually we could achieve. So if you look at this, this is the internal variability of monsoon rainfall from 1998 to 2019. Actually, it is extended. I will show you in other slide as well. So the blue one is the GFDL sphere model, and the red one is our monsoon mission climate forecast system version 2, and GPCB is the observation, and CIS5 is the ECNW system. If you look at the scales of these models, what you notice is that GFDL sphere scale is about 0.61, whereas MOCFS version 2 scale is about 0.71, whereas ECNW CIS5 is only 0.55. So once after improving the monsoon simulations in the model, we also notice that not only monsoon is improving in the model, but if you look at NINO 3.4, Western Indian Ocean Dipole, DMI, Atlantic Zonal Mode, Atlantic Meridional Mode, all these skills have improved significantly. So what is the lesson that we have learned is that monsoon just cannot be ignored in the coupled models or atmospheric models also. If you ignore, what will happen is that your circulation patterns will be very much skewed towards some other state. Therefore, the skills whatever you are trying to get are for a wrong reason. This is the one of the important understanding that we have achieved. So, by if you look at that is the reason the why once you have this all these heat sources correctly simulated in your model, so therefore your circulation, that is the winds, are also well captured in the model. So this is one good thing that we have achieved. under monsoon mission, that it is very important, and it also will actually ensures that the skills improves not only for monsoon but other regions as well. So this is the acid test of the models. So here we are not done any indicators. Whatever initial conditions are used for forcing the models, that same initial conditions are used for both MMCFS version 1 and also version 2. So what you notice is that version 1 skill is about 0.6 and version 2 skill is about 0.74. Here you can see that different models are listed, and all these models MMCFS version 2 stand very clearly out of all other bunch of the models. So these are the statistical model predictions. This is the dynamical model of IMD. What the IMD does is that they also take CFS version 1 model and add other components, try to give a forecast. So until 2015 or 2016, they were using only CFS version 1, but afterwards they started using the multi-model ensembles. So the skill actually is 0.45 only. So using instead of several multi-models, if you use only monsoon mission models, the skills are definitely far better compared to using multi-model ensembles. So in the MMCFS version 2, I promise that how the teleconnections have improved. So this is the 3.4 teleconnections with all India summer monsoon rainfall. The observation is about 6.64, whereas in MMCFS version 1 it is about 0.83. That has reduced significantly in MMCFS version 2. So this is one of the important reasons why the monsoon prediction is improving in the models. So if you look at different homogeneous regions, you also see that the monsoon simulation is quite good. The MMCFS version 2 JJS mean in also different month-wise distribution is also there. What is that you have to understand is that variability, internal variability is also very well captured, not only for JJS but July or September. Somehow we miss June month variability, not captured by the models very well. Okay, so this is again skills for different regions, homogeneous regions over Indian region, and again MMCFS version MMCFS 2, almost all regions are doing better except Northeast India. That is where we have still problem. Northwest India, sorry, not Northeast India anyway is not good for both MMCFS version 1 and version 2, but in the Northwest India, we are actually MMCFS is not doing very well. So if you really look at the potential predictability of the monsoon in CFS, so Prashant has written a paper in 2018 that he has shown that 0.7 is the potential predictability limit in the MMCFS version 1. And when you look at the real prediction scale, it is only 0.55. So this is the potential predictability limit, and this is the what is achieved. So there is a big gap between whatever it could be achieved and what is achieved. So if you the new model, again they started looking at what is the predictability limit is about 0.79, because many components are changed in MLCFS version 2. So whereas the actual scale is 0.72. So they are coming very close to each other. So the gap is actually decreasing. If you remember before monsoon, the gap was huge, that was started decreasing. That is another big achievement for the models. So now the question is that if you start using that is, so far I talked about only the seasonal predictability limits. If you look at monsoon interseasonal oscillations, this is the standard deviation of monsoon interseasonal precipitation. So you can see that there's a big blob of very strong variation that over the way of background. If you take that and try to create this Lyapunov exponents, we can get an idea about what is the potential predictability. Actually, it reaches up to 40 days over the wavelength. But if you look at other dynamical models, by day 3, but that is over this region. Actually, week 3, by week 3, that skill, after that, it drops. So this is, there's a lot of, again, in the seasonal, sub-seasonal, still some gap is there, so that the people are working to improve this as well at IITM. So what is the scope for improvement? So what is that? What we have tried to understand so far about the monsoon, and what is that is essential to improve the skills to whatever we have seen now, resolving the small scale process, both spatially as well as temporally, that is most important. So for example, spatially, you need to, for the oceans, you have to resolve the eddies that are present in the oceans and its impact on different atmospheric convections, and also the rainfall, we have to get it properly. So just increase the resolution is not the only solution. You have to understand the process very well and make sure that the process are actually incorporated in the models. So now improve the initial conditions. So there are a lot of uncertainties in the initial conditions itself. So that actually makes a lot of errors in the models. So what we propose is that start initializing the land surface and also start utilizing coupled data simulation. Most importantly, represent the ignored components in ESM. So dynamical station is one of them. Interactive results chemistry, BGC, ocean biogeochemistry, and waves, etc. should be started. We should start incorporating them. Then we can expect the predictability gap that what we see, the little predictability gap that we see today, can be actually filled in as well. So now everybody uses AML models, and if any talk completes without that, means it is an incomplete talk. So what we try to show is that this is one paper published in 2024, and they have actually used almost all AML methods and try to see which one does very good. They came up with LSTM model that has some information about Nino and also MOD that gives you a skill about 0.72. So this is what is the AML model can do that. If you consider only this both ENSO and IOD into your model, then you can get this much of information. So whereas if you look at the Delco model, it is already there or slightly better in the models 0.72 with the initial conditions, February 0.56, 0.7, 0.66. So like that actually has shown significant improvement, particularly in the month of April initial conditions, you get 0.72. Once you come to May, again there is a lot of signal to noise ratio problem. So it starts actually decreasing the scale as well. So same thing if you look at MISO forecast skills, again in the ML models, again you see that uh, about 28 days, that is the you can get good forecasts for the September initial conditions, whereas the rental model has not separated out them accordingly. But what you see is that there is a lot of improvement to 21 days in the latest version of prediction range forecasting system, prediction system of version 2. So both actually, if you actually put a lot of efforts in the rental models itself, so you are able to achieve something which is AML models are achieving. But you will ask me a question back saying that running AML models is much easier and faster. So why do we need such dynamical models? The reality is simple. So you know what is happening in the dynamical models. So why the prediction, why that prediction has come is expected to be like that. So whereas in the AML models, most of the information you may not have it. So cannot track the physics back to try to understand what is that happening. So, but at the same time, I'm not trying to discourage or I'm trying to advocate only the dynamical models. You need to have the combination of both of them. If you ignore one model's dynamical system completely and try to develop AML models, then you will not get much of improvement as well. If you again without using AML, if you try to do everything using the dynamical models, then also you will not get. So you see that there's a gap is there, small improvement is happening by using the AML models, at least at sub-seasonal scales. And if you come to the weather scale, the gap is much bigger actually, and you can get better forecasts up to 5 days or 7 days over the monsoon region. So message is that you have to use both of them, but try to understand what is actually improving your the skill. That is with that I stop my presentation. Thank you. So it took 2 minutes extra. That's all.
Anybody is having questions? Thank you. Very interesting. I wonder, do you have, you also mentioned data assimilation. Um, which form of input or which form of data do you think is the most information to improve?
Yeah, what though we don't do much of research and data simulation methods are the observations that go into that data simulation. Our sister organization is there in Noida, that is NCMRWF. What they have shown is that surface observations and the radio sound observations contribute significantly for improving the forecasts. That is what they have shown. No questions.
They are your people only, so they can ask.
So they are asking, they are afraid to ask or what? Okay.
There is no question. Thank you very much. Next lecture will be by Dr.
কতক্ষণ লাগবে তোমার? আমিও
35 slides হয়েছে টোটাল, যদিও ছোট ছোট করে
আমি তো 1 ঘন্টা ভেবে ইয়ে করেছিলাম, মাত্র কাজ শেষ করে নিলাম। চলো তাহলে আমি শুরু করবো নাকি?
হ্যাঁ
Thank you, and good afternoon to everyone. So, I have summarized some work what we have been doing here in IITM. So I'll talk about something about land atmosphere interactions, um, focused on Indian summer monsoon, um, how it affects variability of rainfall at different time scale. And when I talk Indian summer monsoon, it's basically June to September month rainfall. And I'll be talking about basically what is the local effect, regional or local effect, how the locally land atmosphere interacts. And also I will add here that how the remote land surface process, they affect monsoon through atmospheric bridge or teleconnections. And just for everybody knows that monsoon rainfall is not a continuous event. It comes as it is a kind of it comes as a pulse. It is an oscillatory phenomena within the season, which are called active and break phase. Active means when you have a rain phase, rainfall phase, and then when you have no rain or little rain, so that is the break phase, and we call it monsoon intraseasonal oscillation. And so land surface is the potential source of monsoon predictability. It is known for a long time, but the biggest challenge we have that we have a lack of data, particularly subsurface data. We have very few observations. We have satellite observation, but that gives only your skin kind of surface conditions. But with the memory of land surface, basically they lie in the subsurface, and that data is not available. um, Only few stations, and it is land surface, very heterogeneous. So it's very difficult to understand. Unlike ocean, it is very difficult that how land atmosphere interaction takes place. So model have been the tool, very useful tool to understand all those feedback. So this is a schematic of how hydrological cycle works, and basically the energy and the water, they are interlinked. Um, so you can see here that a major portion of precipitation which falls over land, it is returned to the atmosphere again through this mechanism, and there is a lot of exchange of energy. Okay, and some estimate, this is from model of course, and it shows that about 65% of total precipitation over land is returned to atmosphere. So you can think of that the huge amount of um, feedback is in play, and we know a little bit but not everything. Another study what shows that it is basically from some isotopic analysis. What they say that what is the amount of evapotranspiration? Majority comes from transpiration, that is vegetation, which is 80 to 90% estimate. So from this perspective, we can understand how this cycle, the moisture recycling takes place. This can give us some clue about the feedback. So what is moisture recycling? It is nothing but that when you have a rain, some part of the moisture get evaporated and then again come back as a rain of the same over the same region. This is called recycling, and it is defined. Recycling ratio is defined by recycled rainfall by total rainfall, and it can be estimated in a various way. Some model, WRF kind of model also can estimate, and also some diagnostic methods are there. We have used LTR and BRAS diagnostic method on seasonal time scale, JJS time scale. You can see the recycling ratio. We have a recycling ratio of about 15-20% was central and North India, but south you can see there is almost no recycling. And if you go to the Tibetan plateau, it is quite high. So this is the Indo-Gangetic plain where things get very interesting. And if you can separate this rainfall into what is the recycled component, what is the affected, and what is the total, what you see here, that this is the affected part. Affected, I mean that this moisture has come from other than land. It has come from ocean. And then recycled rainfall, that is what is recycled within this land surface. So one thing we should remember, that recycled rain is not independent of its own. It is a part of the large scale. For example, when monsoon starts, it is dry, but when you have a rain, it's of course affected moisture, and then as things starts, some recycle there, and then some moisture comes from outside. So that is the affected and recycled rainfall, right? So you can see there's North India and Himalayan region. We have a lot of recycled rainfall here. And then we try to understand the modes of variability in recycled rainfall, because this is related to local feedback. So what kind of modes we have? So you can see the UF 1, 2, 3 mode. UF 1 is quite strong, 38%. This is second is a 14%, and then corresponding PCs. Interesting thing is that you have a PC2, which is showing some decreasing trend. This is from I think 79 to 2014, I think. Yeah. So it is showing interestingly decreasing, and we know this region we have a decrease in rainfall in recent last few decades. So further, if you can we try to understand that we regress the PC of this recycled rainfall with advected rainfall. As I mentioned, that some part of advected rainfall, they are interlinked with recycled rainfall. So when you regress PC1 of the recycled rainfall with advected rainfall, that you get here. So that means very strongly PC1 is strongly related with advected rainfall, first mode. But if you see the second mode, which is showing decreasing trend, you don't have a strong relation. So that suggests that there might be some modes of variability independent of large scale, and it is within the system. So it is commonly seen in a couple system that some modes are variable couple system, nonlinear couple system. Some modes, they give rise to some modes which are independent of these large scale forcing. So probably this is the one. And if you see the large scale monsoon circulation, this is the mean rainfall, and you have a this contours are basically the wind circulation. You can see the mean structure is such that it converges all this evaporation from here to this part. Okay, so it is a region of convergence of all this evapotranspiration, what is happening on land. And this is the trend, what you see in 100 plus, more than 100 years of rainfall from IMD over India, and the rest of the place from CRU data. So you have a clear decreasing trend over this region and increasing over rest of the India. And if you see the box in details, you can see this is a decreasing multi-decadal variability, and then recent decades you have a very strong decrease. On the other hand, western side, you can see this is persistently increasing with some multi-decadal variability. So this has been, a lot of research has been done to explain why this kind of behavior. Um, Global warming, we have seen, we have heard in morning lecture from Dr. Krishnan. Global warming is expected to enhance monsoon rainfall everywhere, right? Because moisture is increasing, water holding capacity is increasing, so it is expected to increase everywhere. But you have some asymmetry, and that indicates also there is a no, it is not a simple thing. There is a complex land atmosphere feedback is going there, and probably there are competing effect between local and large scale external or global warming. Okay, so we try to see the trend in this component. Total rain for recent period, because recent period we have some IMD observation I will show in a minute. So 79 to 2014, you have a still decreasing trend over this region, decreasing this region. And if you see the recycled rainfall, it is also decreasing over this region. Advected trend, you have a mixed structure, some decreasing, some increasing. So this estimate is based on ERA reanalysis, where we use a evapotranspiration from ERA and Q and vertical integrated Q. U, V, and Q are all levels, and then we make the what is the amount of moisture available, but in a vertical indicator sense. Okay, so in EDA, however, I don't have here. However, in EDA, we don't have much trend. But if we see the observation, this is from IMD station observation. This is evapotranspiration based on lysimeter. This is pan evaporation from IMD, and this is the wind speed. You can see all are decreasing in last from 79 onward. They are decreasing, and all this cross you see, they are significant, statistically significant, more than 95%. What observation shows that ground wind is decreasing? Okay, and then pan evaporation. There are a lot of papers. Even globally, we have a decrease in pan evaporation. This is specific to India here. So it is also decreasing. And if you say the area average, all are decreasing. And if you can read the number, it is around 100 millimeter decrease in evapotranspiration in 37 years. And what we see in a rainfall decrease is more or less on a similar figure. So, so it is possible that some feedback may be modulating this decrease in rainfall. So, as I mentioned, that ERA data we have used, and there evapotranspiration, we don't see any trend, although we see very strong decreasing trend over in observation. So, what we did that we used evapotranspiration from observation, IMD observation, interpolated in a grid wise, and estimated again the recycle and affected rainfall. You can see much increase in recycled rainfall. This is from NOAA 20th century analysis. This is from ERA. So you can see very large increase over this region, and also you can see increase. And these regions may be probably due to irrigation. There is a lot of irrigation in this region. So maybe this observation has picked up those signature. So what it is suggesting that that you have a very heterogeneous characteristics of land over the monsoon region, and probably there is a competing effect that global warming trying to increase rainfall everywhere, and then local feedback is trying to reduce this. What is the mechanism? Probably it is due to decrease in wind speed. It will also, this evapotranspiration decrease depends on various factors. One is important is the wind speed. If you have decreasing wind speed, so it will decrease the evapotranspiration. So this is a hypothesis probably that this way it is going. Once you have a slowing down of circulation, what we see from observation, it is going to decrease your evapotranspiration, and this evapotranspiration is affecting where you have more recycled rainfall, particularly this Indo-Gangetic plain or northern India. You have a lot of recycling here. So, one hand, global warming trying to increase everywhere rainfall, and on the other hand, due to slowdown of circulation, it is decreasing the rainfall over Indo-Gangetic plain, and then as a result, what we see that decreasing somewhere, increasing. So this is the first part. Then I'm coming to the MISO, monsoon interseasonal oscillation. So we asked ourselves the question how MISO interacts with land surface. Okay, so one of the important component of MISO is the climatological ISO. So they are actually phase locked with the annual cycle. So I'll show you the picture. So our hypothesis was that if it is phase locked and we have a big transition from pre-monsoon to monsoon, land surface condition changes drastically. So there might be some, if there is some perturbation, initial phase of monsoon, they can change the feedback, land atmosphere feedback, and eventually they can modify the CISO, which can give rise to some variability even in seasonal time scale. So what you see here that from IMD observation, monthly composite of internal component, that is 10 to 100 day filter rainfall you take, and then average over month or all the year. So you have a average picture of ISO, what is called climatological ISO. In June, you have central India, you have positive phase, and then it goes up. So like this. So we asked that if we have some perturbation here, beginning once June month, we have 1st June is the mean climatic mean onset over Kerala. And then you have some perturbation in this beginning, say due to some convective activity, maybe due to MJO or anything, whatever. Okay, so how it can affect the ISO, and if it is able to affect, what is the impact on seasonal rainfall? Okay, so how to do this? How to test this? So as I mentioned, that we have a model is a tool what we can use to test our hypothesis. So we use a regional model in this case because it is very useful. So that by design, the experiment was that you use the regional model and force your boundary condition repeatedly year by year, and then see if there is randomly some initial perturbation is generated in the model in the pre-monsoon time, and if it is generated, then how it is affecting CISO. That is the idea. So we have done from 82 and 89. We have chosen 82 was a dry monsoon year, 89 was a normal monsoon year, and we have run for 31 year, just repeating the same boundary condition, and see what is how the internal variability is inside the model. So this figure is basically x-axis is the time, 15th April to I think 11 October, and y-axis is the variance of Central India rainfall. So in 82 we can see it has created some variability, internal variability on pre-monsoon time. This is a pre-monsoon time, and but 89 case you don't have such thing, but you have a strong MISO variability on the rest of the season. 82 we don't have MISO variability. So that was the ideal case for us to internally generated variability, how they interact with land and atmosphere in two different cases. This one is for CISO and other for ISO. And then if you have some statistics, how was the mean and variability, all those things. Now, if you look, we try to first pick the signals, very strong dry year and strong wet year from the monsoon simulation, and then try to see how this accumulated rainfall is evolving actually. So we have a two, if we say the dry and wet year from this bar, all India rainfall, all India, I think all India, probably all India. So we have a clearly these two are separated, and if you look zoom into this region, this time zone, that pre-monsoon time, you have a clearly you can see that dry year followed by wet condition, wet year followed by a dry condition, and if you have a number here, wet year you have 39.49 millimeter, then dry year this much. So, but that gives you very strong difference in first phase of monsoon month, that is June. So why, question is why we get only here, not other place? So that maybe because of some we are using same boundary conditions, so we don't expect much difference in other month because you have a clear variability in this pre-monsoon time. Now, if you look at CISO, CISO is nothing but the filtered anomaly, and 20 to 100 is filtered central linear rainfall anomaly. This is the all year composite. Yeah, this is the time y-axis, and this is the wet year composite. You can see the pre-monsoon time, you have a dry condition, right? And then it gives a huge wet condition, and then rest of the things as usual. Okay, the dry year composite also, you see there is anomalous wet condition, and that have suppressed this phase of monsoon rainfall, and that has affected because it is a controlled one, very controlled one, that has effect on seasonal rainfall. If you like to see the spatial structure, these are the soil moisture difference between wet and dry year. You have a large scale deficit of soil moisture, and if you see the time series, it's very quite drastic. Similarly, air temperature also you can see large. There is a 1-2 degree temperature difference in pre-monsoon, and that can give you seen also in time series. So to summarize that, we propose the new mechanism through which the CISO can be modulated through land atmosphere feedback. Of course, in the first phase, and that can generate some variability and contribute to the seasonal rainfall. So this studies has implication that if we have a forecasting system, the accuracy of May soil moisture for particular seasonal forecast will be very important to seasonal as well as sub-seasonal component forecast, May soil moisture will be very important for the accuracy of the forecast. Now the second part, that understanding the mechanism on the sub-seasonal timescale within the season, how the MISO is interacting with land surface processes. So we put forward hypothesis from observation. So observation, we asked that do we see in observation any signature of this kind of feedback? So we picked some strong MISO events and weak MISO events, and try to see in the composite. This is a filtered composite, and this is the actual rain. What do you see that the strong, of course, it is a strong, it is a zero lead lag actually. So what is happening before and after? So before that, you can see that weak ISO and strong ISO, there is a significant difference in rainfall. There's 95% significant difference in rainfall. Even if you see the atmospheric stability, there is a for strong ISO, there is atmosphere is highly unstable. Okay, so the hypothesis was that probably there is a feedback, land atmosphere feedback, and we all know that MISO, they are basically atmospheric mode, but when they travel through ocean or land, so they are modulated by boundary condition like ocean and land. So to what extent it can modulate the MISO, that was we try to understand from this model experiment. And the hypothesis was a one-line hypothesis that a strong break phase is followed by a strong active phase, and we'll see whether you can see in model. So this is the feedback loop. We try to make it simple. What is happening in active phase? What is the break phase? So if we start from active phase, the amplitude ISO, a more stronger ISO is more rainfall, so positive feedback. It will have a kind of memory in soil, and then if you are wet, it will reduce the sensible heat part, all those things. Again, affect the active phase. So like this, active and break phase, they are interlinked. So that is the schematic of feedback. And now let's see the result. That what I mentioned already, that this is the time axis, 1st June to September, and this is the year, 31 year we have done the experiment. And you can see that these are positive phase and these are break phase. Actually, these are active phase, these are break phase, and they are phase log because we have used same boundary condition. Same boundary condition, so large scale information of MISO remain same. So we have a solar same phase, but there are a variability within this. Okay, you can see. So you can really connect strong, if you have a strong break, so strong active like this, you can connect. So there is some evidence here that strong break phase is followed by a strong active phase because of land atmosphere feedback. So to confirm this, we further did the experiment that you have a soil moisture for I think central India, kind of like this, the red one. So we prescribe the smooth annual cycle of soil moisture. So when you prescribe a smooth annual cycle, you don't have variability during active or break phase, and then try to see how it is affecting the monsoon rainfall. Okay, so what you see here, that sensitivity minus control, that mean circulation has decreased, it has become weaker. 850 hectopascal and 200 hectopascal, because this is the closed system. So if this is decreasing, this will also become weaker. And if you look the MISOs, actual MISOs, strong and active MISOs, you can see clearly they are becoming weaker. So there is a land atmosphere feedback on international time scale in play, and we summarize that based on summary based on observation evidence that we propose, that strong break is followed by strong active phase. Okay, so we carried out some sensitivity experiment with model, and then found that there are some feedback exist in this system, and this is the inherent to the system, this coupled system. And we should have a when we talk about subseasonal forecast, we should have an initial, probably Rajiv will talk, initialization becomes, soil moisture becomes very important. Now coming to a remote influence, if I have remote influence. So remote influence, we have I can give you two examples. One is Eurasian snow and Tibetan plateau. They remotely affect the monsoon. So I will present only here Tibetan Plateau. This is again one paper by our group that what we did that we have, if take the center, as I mentioned, we don't have soil moisture data. So we use rainfall as a proxy. So we take the central India rainfall of June and then correlated with the rainfall of everywhere of April, May. So spring rainfall everywhere correlated with June rainfall of central India. What you see here, very strong correlation over this region, northwest part. This is Afghanistan, Iran, all those region, heat low region, and then you have positive correlation. If you see the temperature, so central India rainfall of June correlated with April, May 2-meter temperature everywhere, you have very strong positive correlation. Okay, so this gives some kind of variability in the first page of monsoon. That was one work by Raital. Then another study by Yu et al., Yongkang Yu. So what they did, there are several studies using Tibetan Plateau temperature as well as moisture. But when it comes to elevated region, temperature becomes very important because this region don't have much moisture, but temperature is very important. So if you have a signature of some soil temperature in land, that may affect your atmospheric heating. So they did a MCA analysis with spring May temperature over Tibetan Plateau, and then how rainfall is linked with the June rainfall linked with the station. You can see dipole structure along the Yangtze River linked with cold R1. This is the actually oscillatory phenomena. So this variability gives rise to this kind of dipole rainfall over the east channel. So both are linked with it, somehow linked with the elevated region. So we asked, we looked into carefully, and we all know that how the mean monsoon looks like. If we look in the May rainfall, so we have already onset Asian region, May, and some onset rainfall, some rainfall over Bangladesh, and then when June comes, it covers entire country. Okay. If you see the variability standard, internal standard deviation, you have a lot of variability because it is our beginning phase May, and then June also you have a lot of variability here. So what is important to understand that the monsoon is a large scale system, interhemispheric circulation. So often we try to separate in the by political boundary, South Asian monsoon, East Asian monsoon, but they are actually dynamically linked. So we ask that Tibetan Plateau is a elevated heat region. So is there any common mode of variability which is affecting both Asian monsoon, South Asian monsoon, as well as East Asian monsoon, which we have seen in 2 independent studies. Okay. So easy thing is to do that. UF analysis of rainfall, do you see in the signature here? So UF of say 119 year rainfall, you have a UF 1, 2 and 3. UF 1, you have a monopole over India and then dipole over this timeout. Okay, I'll finish it. So what I showed here, dipole structure you have here. So, and it is capturing both actually. And if you see the PCs, none of the PC is showing any trend. So it is a robust kind of modes of variability. And if you link with this more PC1 with the temperature, surface temperature, 2-meter temperature of May, April, you have a strong correlation here, positive and negative correlation here. And also, if you have a temperature average over this region, correlate with monsoon onset, Kerala onset, very strong correlation, robust correlation. Snow water, this region actually have a lot of glaciers, mountain. So of course, land surface snow water, if you correlate, is robust, very robust correlation. So this looks very land atmosphere. This variability is created over this region because of maybe due to land atmosphere interactions. And we have done also May June rainfall because one can ask that onset over East Asia is in May, so why not to do May June? So when we use May June rainfall and UF analysis, so both looks similar, and then teleconnections also more or less similar. Now the mechanism. So there must be some physical link how it is happening. So if we regress this temperature of Western Tibetan Plateau, the box with vertically temperature, air temperature and omega, you can see month wise, strong ascending here, ascending motion here, anomaly, regressed anomaly, and then temperatures are also very strongly correlated. Monsoon season, you see the dip, and this is probably when monsoon sets in, it dominates. Its heating, its influence dominates. When monsoon retreats, again this heating picks up. So they are in play throughout the year. This feedback, they affect the troposphere. And the other question I was trying to, that you have a correlation positive here, negative here. So it is possible that you have a convection here in May. That convection gives rise to heating of a troposphere. That may be seen here, some you may ask. So we try to understand that who is first, whether this heating happens first or this one, some convection activity happens. So if you see the annual cycle of temperature of this region and the rainfall of this region, the temperature starts actually early. Okay, and if you see the lead lag correlation, this is a 50 days ahead. This anomaly happens, and the tendency also shows similar things. So definitely this happening first. So they attract monsoon circulation. The convective activity starts building up because of north-south temperature gradient. Then what you see the onset progression. Okay, so this is not only the local effect, but it has some global impact. So this study recently published in not recently but 22 that shows that not only Tibetan plateau but the Rocky Mountain, they are in some kind of synchronization, that they are elevated kind of heating, and they trigger some kind of stationary waves, and they have a if you T index, TPR Tibetan Plateau Index, and RMI Rocky Mountain Index. They are in some inverse correlation. Similarly, if we regress Western Tibetan Plateau temperature with May geopotential height, June geopotential height, you have a strong, significant stationary wave, kind of wave, and that wave is affecting also East Asian, and perhaps it goes beyond. Okay, so if you regress with PC also, you can see similar kind of structure. So it is a triggering probably planetary scale circulation, and that is affecting remotely in a region. So I'll stop. I'll not go in the model. Rest is the model. We try to investigate how the model, it is a simulated model, and most of the model, most of the now all model fails to capture those things. Okay, so summary that we found the dominant mode of variability in June rainfall over entire Asian summer monsoon region, and this is linked with the spring land surface temperature over Western Tibetan Plateau. Okay, so finally, to summarize that understanding land atmosphere interactions remain challenging, as I mentioned, primarily due to lack of surface observation. So often we use model to test our hypothesis. And the potential influence of land surfaces in weather and climate is probably not utilized fully, because we have tested recently one I have not shown here, that when you don't initialize land surface in seasonal forecasting, we don't have any change in skill. So basically it is not affecting anyway skill. So we are not able to probably exploit those predictability arising from land surface. So we need to have some improvement there. Thank you very much.
Yes. Okay. Happy to reply. And now I request
Thank you.
Dr. Raji deliver the second part.
Yes. It's currently for the planter.
So in this particular work, I want to continue the thing, but it would be much more focused on a particular aspects which you will be seeing it, not a broad overview. So a part of this is already published here. So mostly this and some of the other things which we are currently working, that will also be reporting here. So this particular work, as you see, IITM is trying to implement better land surface process, and in order to exploit this predictability. So again, I am starting with the question that what is the nature of soil moisture feedback to the subseasonal variability of rainfall? And but as you know, we are so in IITM we are also trying to improve our forecast skills. So whether this forecast skill will be based on operational model, which is the CFS, NCEP CFS. So this understanding can improve the forecast skill in the model. So when I talk about forecast skill, I mean this. So suppose this is active spell, which is starting from. So this is active spell, and this is rainfall plotted 5 days before, 4 days before to the peak active spell. Okay, because last lecture you have heard active spell, so that means extreme rainfall. So what is the problem in the model? The problem in the model is that you get lot of dry bias over the central Indian region, where actually there are a lot of rainfall, and this dry bias actually persists few days, and then again becomes weaker. But there is a when there is a peak, so that means that if you are trying to predict the active spell, there is going to be some problem. Now, let us recap some, say again what you have heard probably. So there are, like, this is the very, what is intraseasonal variability? Okay, so intraseasonal variability means you have a rainfall annual cycle and you superimpose the high and lows over this thing. So you will get a certain low frequency oscillation, which if you make a power spectrum like plot, which comes as a dominant peak. Okay, so this is called the intraseasonal oscillation peak. Okay, this. So what we are trying to understand is this peak. The second part is that this oscillation, which is a time series aspect, the spatial evolution is also very interesting. The spatial evolution, if you start from 15, 25 days before, you will see a nice evolution of rainfall from 25 to this thing. So which increases. So first the rainfall starts along the equatorial region, and then it moves northward region, and then there is a strong rainfall established over. So which is called the peak active phase, you can tell. Okay, and then again it diminishes. The opposite phase that time formed. So this is the spatial extent of the intraseasonal oscillations which we are looking. Now, uh, uh, this interseasonal oscillation has one important aspect which I would like to mention is that it is first is, suppose this is Whaler and this is vorticity at 850. One thing is the way there is a, and if you plot, this is the Hofmuller diagram. So if you plot this Hofmuller diagram from -3 to 30 to 30 day time, so with 0 is the peak, so you will find some phase shift. Okay, so phase shift of, so this is Whaler and this is vorticity. So vorticity leads the convection. So this is one of the important aspects of interseasonal oscillation. Of course, it is known for some time now. So then so how intraseasonal oscillations are impacted? So I have noted some factors from left to right. So this is local versus. So there are a lot of studies going on in various ways, including. So how interseasonal oscillations are impacted by this. One of the significant improvement we achieved in our model is by improving our sea surface temperature. So what we find is this is the rainfall at lag 0, and this is the sea surface temperature or net heat flux. So you can see the there is a definite lag between sea surface temperature and the peak. So this has exploited, this aspect has been exploited to understand the predictability, because SST gives this predictability of the interseasonal oscillations for some time. Now coming to the, so the context is like, the context is here, of course, we are interested in the land surface part. So the context is like, uh, yeah, so as you are hearing from the morning, so there is two aspects. So like one is the physical components, is the precipitation, transpiration, and many other components. So there could be dynamical aspects and there could be thermodynamical aspects. So the way it is modeled here is like land surface. So if we focus on the land surface, so land surface impacts the boundary layer, and that boundary layer impacts the rainfall. So this is the way in which it is modeled in most of the, if you say, dynamical models. So now for the model which we use, this is a schematic we obtained from this website. So which says that this tries to incorporate all or many processes, including some of the processes which are like purely boundary layer property, like turbulence and all other things. So these things are modeled, and these things gives finally the rainfall of the interseasonal oscillations. So it is clear that if we are trying to understand this land surface, then we cannot omit the intermediate step. So because this is how if we have to get a better prediction, it's not the one component should work better, rather one feedback to the other, feedback to this, and then again it is feedback to so the whole loop has to work better. Now, there are different ways to define. So in the next whatever we will be discussing this on the basis of rainfall, for example, as the indicator of so active break phase, for example. Also, the intraseasonal oscillations, we call it as monsoon intraseasonal oscillations. So we actually, how we define it in a mathematical way is we take the rainfall extended EOF. So what happens is that if we take rainfall up to few, so there are many methods. This is one of them. So in IITM we are using this. So if we take rainfall from 1 day to past 7 day, and then we put it as in a covariance matrix, then we eigenfunction analyze it, and then we get the dominant variance. So this is the first two dominant mode gives the interseasonal variance. Why? Because if you remember the power spectrum, so the principal component gives the power spectrum in that range. So how it looks like, because I have showed the filtered composite. Now from the MISO, you can see that if you start from, suppose, any phase, from phase 0 to phase 1 to, you will see there is a clear propagation of rainfall here. Now so if we start in a simple coupled view, how this evolves to understand it, so we can think of like this. So this is this is the P minus E equation. So precipitation minus evaporation is the vertically integrated moisture, and the atmospheric term, which is defined here, which is the convergence and the divergence of moisture. So then there is a term, we can call it as the land surface term, which is the rate of change of soil moisture is this. Similarly, there will be a temperature, which I have not shown because just I am trying to emphasize the coupled part. So then this is coupled via, one way is coupled via this is evaporation term, which is the difference of this between gradient of surface soil moisture to the boundary layer soil moisture, and these wind speed at the surface. Okay, so why I am saying it. So similarly, there will be a temperature or other terms which will be coupled to the temperature equation. But the point here is, so this is coupled to this. So if we replace this term here, we directly link land surface to this part. Okay, so over land, for example, the evaporation is estimated in a very simple way. It can be estimated based on some critical value. It is the E0, and then if it is less than critical value, then it is a fraction of that. Okay, so you can see if we directly couple with land surface to this through this type of nonlinear relationship, it creates a relationship very complex. So if you change a part here through evaporative coupling, depending on the availability of water critical, the response time switch response actually changes. So other than that, also, if you see that there is a dynamics part, so the dynamics part is the mean background part and the transient. So mean and the transients also force the evolution of this moisture. So this is one of the classical old paper by Peter Webster, where actually when we have seen this paper, so most of the important hypothesis of monsoon intraseasonal oscillation was actually given here. So here is one of the first reference I get where the land surface hydrology, he clearly mentioned that the surface hydrological effects are very much important for the monsoon intraseason also. So most of the conclusions which we started, you can find it here very interesting in terms of sensible heating. So what he said is the sensible heat input to the boundary layer, then it destabilizes the boundary atmosphere ahead of the ascending zone, allowing the moist convective component to move northward slightly ahead of the band of precipitation. So if it is the land surface, yes, so this northward propagation which we have seen, and then later there are a lot of theories based on you can say like background between interaction between the barotropic and barotropic by Xiang et al. And then from IITM understand. But even before that, when they are claiming that that is causing the northward propagation, this study shows that the land surface hydrology, and these papers clearly get the scale selection in the intraseasonal mode. Okay, and there is many other important conclusions which we are still using. So one of the, and even we find that this is the Vichy theory which gives MGO eastward propagation. It came in 87. Even so it's the same. It gives the eastward propagation. So it's even came before that. So this is one of the way we can think of how land surface hydrology is important here. So now another way of showing it is this, that you have Nino 3.4. If you plot the rainfall average between the grid box where you have temperature over the Nino region, you see this is the rainfall, average rainfall. So or the Bay of Bengal, and this is over some different two types of sand and clay region. Okay, so if you see that these are completely opposite, rainfall response is completely opposite. So it means that to get the idea of a proper land surface process, we need a different approach and different way of understanding how it works. Okay, now what is that? What we are talking here is, so here we see that most important observation is, so suppose this is the rainfall composite where you see a clear northward propagation of rainfall. Okay, and then if you see the soil moisture propagation, the soil moisture propagation, if you see, it is also propagating northward, but there is a clear east-west gradient. Okay, now in the phase 3, when the phase is over central India, the rainfall is more or less uniform here. The soil moisture of 0 to 7 centimeter clearly shows that this is in this side there is a excess, and so there is a gradient, so it does not move homogeneously. So in terms of soil moisture, this is one important feature which I'll come latter. So this is the first thing which we noted, that in addition to the temporal variability which Dr. Saha has discussed, during intraseasonal oscillation propagation, there is a east-west difference in the propagation of soil moisture. Now coming back to the dynamical part again, so these are the some of the way we give the rainfall, and then we give the power spectra, okay, different years, okay. So every year we see some peaks in the intraseasonal oscillations, okay. Similarly, if you see the soil moisture at the at different level, I think the first level is already given. Yeah, level 1 is the 0 to 7. So you see the interseasonal peaks which are more or less conforming to the rainfall. Okay, so there are interseasonal peaks. Now, as you go deeper, what is happening is, if you see that this is actually it is shifting more and more, power is more and more shifting towards the low frequency high time period situation. So the deeper layer soil moisture gives much more slow response, so which is a part of actually long memory. So this can be linked to the predictability, and there are several studies which shows that, for example, Lemias in 1952 has shown that the persistence increased. So land surface has a slow time scale and atmosphere has a fast time scale. So if you couple these two, and also there is a chapter by Vallis which shows this thing clearly, the spectral shoulder broadening, which happens because of the coupling. So so increased temporal persistence of the fast time scale can be this chapter by Sukla actually means concluded this seasonal, but they concluded for seasonal that seasonal can be increased by realistic initial soil wetness, because the slow time scale, if we get the more slow time scale better, then the fast time scale would be much more controlled by it, and then we can get a better predictability. Now, these are the studies which actually shows that the autocorrelation function with the time, which is important, which is a function of seasonality of the atmospheric portion, but also it is a function of the different functions of the soil variability, like runoff, okay, coupling between soil moisture and substrate. So these determines the net autocorrelation, which is giving you the slower the or fall of the autocorrelation, which gives this thing. Some other study also gives that this can cause the rebound of predictability after few days. Okay, so there are studies for that. So this is so it can be seen. This paper can be seen, and they have discussed all this in very details. Okay, so for the CFS, for example, then we have seen a lot of studies on this thing, where we are giving a saying that they have concluded that the surface temperature has a strong cold bias, and this cold bias is due to error in the initial soil anomalies, which appears to be too wet. Okay, and then when this monsoon mission, you have heard from the director, when this started, they said that in some of the exercise in the monsoon mission model, it has shown clearly that there are significant increase in the forecast skill associated with realistic initialization of the land surface. Okay, but they also have concluded one thing, that even though there is a clear responsiveness of surface heat fluxes, temperature, humidity, and this to the variation in soil moisture, the soil moisture is not that much unresponsive. Okay, so sorry, so I cannot see the thing fully. So variations in soil moisture is, and the precipitation in CFS is not fully responsive. Okay, so that means they said that there is some problem in which the soil moisture and the rainfall is coupled, so that we are unable to extract the full prediction scale. Now, this thing you have seen in the previous lecture, where they have said this is the path, the moisture memory is the sensible heat flux. But when we studied there, they have not they have assumed that monsoon region gets large amount of soil moisture rainfall, so which brings soil moisture to a saturation level. Hence, it is any previous. But what happens? We ask the question based on this earlier plot. What happens if there is a spatial distribution of rainfall, and there is a spatial distribution of so there is a gradient. So everywhere is not getting the strong rainfall. So we propose another alternative pathway from here, because soil moisture memory through can be obtained through some fluctuations of soil moisture, which can lead to variations in latent heat flux. So this can give boundary layer moisture and has a role in playing the moist static energy. So next few slides I'll show the evidence. But before going to evidence, I'd like to show why this is important, because RH, the cloud development. So this is this is, for example, one equation which Ekan Hosteger has given. Gave. So this is the change in the relative humidity, which is a function which they're calling as the effective evaporation and non-evaporative components. So it is related to both evaporative and non-evaporative. So there is a competition between evaporative and non-evaporative components, and if one component wins, so it's not like always the evaporative component will be significant, but if it is saturated, for example, for any particular value, the non-evaporative components like sensible heating and other things which are included in this in this terms can also take part, or at dry atmospheric detrainment like that can take part in this part. So the point is that I'm trying to say is the evaporative fluxes should be very important, and uh, and so if this evaporative flux can change the moist static energy, which in the CFS or any mass flux scheme is they start searching for the level of maximum moist static energy below 700 HPA. So this would give the understanding of how we are actually giving the so the moist static energy would be a very important function for this. Now, from observation, let us see how it goes. It goes that, so this is again the lag composite plot. So it starts from 12 days, and this is lag 0. So as you can see, the contours are actually rainfall. Black contours are rainfall, which is strong, which gives the busy contours, which is all over India. But the shading is the soil moisture. As you can see, again, soil moisture is not propagating uniformly over all parts of the country. So whereas this side gives a stronger soil moisture component here, and this side does not give. So if you more closely look into it, there is a very difference between the soil moisture and for the seasonal. So in the seasonal scale, you have a low soil moisture to high soil moisture because seasonal rainfall is like this. But for the intra-seasonal scale, if you remove the seasonal mean and during the active phase, if you make the composite, you will have higher soil moisture here, even though rainfall distribution looks homogeneous over all the regions. So this means that there is an imbalance, or there is a difference in control the soil moisture and this evolution, and that probably gives some control. So to see this in another way, we took two boxes. For example, one box is slightly westward and northward, and this is. So what is happening is we take a difference of soil moisture between north minus south. So this black line is the soil moisture, one model soil moisture. These are different reanalysis or observed. So if you see, the north minus south is a measure. If it is greater than 0 means positive means north has more rainfall than south part. This box. So if you see, when rain at lag 0, the rainfall after lag 0, the north and south rainfall becomes equal. So this is the homogeneous, and rainfall starts increasing from here. But the soil moisture actually have started increasing in the north box much earlier than this. So this is one type of role, because of the spatial staggering of rainfall and soil moisture is causing some type of precondition. Now, why this is, we find that this could be related to the soil type, which we find that this is nicely related to the soil type of scenario. So now then, what is the impact? So impact of slightly more. So on the east side, which we have, sorry, this would be west and east. This is reverse. In the west side, where there is more sand in our Indian region, because of increase in soil moisture, there will be sensible heat. And east side, because there is no change, that much change in the soil moisture, it is staying along there. So I'm talking in terms of intraseasonal anomalies, there will be no change. And because the radiation is still not that much hindered, because rainfall has not started there, so radiation is there. So that has to lead to increase in the evaporative or so it means that if we increase slight soil moisture to this side, so it will create different, based on energy consideration, it will create different type of response over east and west. So as you can see, the temperature has cooled down here. This is the surface temperature. So because there is more soil moisture, the temperature has cooled down here around like 0. This is unfortunately this is red, which is negative, but this is low value. This is cooled down here, and this cooling down has actually so then the, and if we plot the moist static energy, the moist static energy has increased. Okay, so there is an increase in the moist static energy. So what we find is that because of the asymmetric distribution of the soil moisture, which could be probably related to the soil distribution, there is a change in the increase in the moist static energy, which actually gives a organized rainfall over Indian land. Okay. Now this thing, whether it is so this is so whether model is giving desired impact. So as we have did some experiment first from the first from artificially from a WRF experiment, where we change the soil to a full of a sand soil type of scenario. We can see it indeed gives much more rainfall over this region. So that feedback mechanism is correct. Now, how it is in IITM CFS, one thing is this, that the CFS has a very, soil moisture is very poor. Even if it gives a proper annual cycle, the actual bias from multiple type of reanalysis is very poor over Indian region, some of central Indian. So there is a huge scope of improvement for this type of annual cycle. The other thing is, if we do a free run, what we find is, remember, this is where you have more soil moisture before this thing. What we see is the rainfall and soil moisture follows each other. So that means there is no lag lead relationship between the rain. So one is driving. So if you have more rainfall, you have wet soil. So there is no lag lead relationship in this case. So so this is same in the spatial pattern which we have shown here. This is same in the spatial pattern. Okay, so now if we do the real-time prediction also, we have shown here that in the prediction mode, this is the dry bias which I have shown earlier, and there is a strong dry bias, negative soil moisture bias, and they are probably coupled. How I am showing you. So the coupling is like this. If I take at lag 5, this is the lag 5 soil moisture and rainfall at different lags. So this black curve is the observation, and these are the different versions of the CFS model, which has used different microphysics scheme and all everything. You will find that all have much more strong correlation as compared to the observation. So this is my, as in the morning, in the first lecture, director was saying that they are much more overconfident. So they are much more coupled to it, and at the previous lag. And when it is at the current lag, although the relationship is simulated well properly, but at the earlier lag, it is not correct. Okay, so this means that we can say that the coupled evolution of rainfall and soil moisture as a spatial shift. And such phase shifts are not represented in model either in the free run or in the forecast runs. So because the moist static energy is not well represented in the dry this thing, there is a problem in the convective rainfall probably. And CFS studies also showed lag insensitivity. That means when you are not supposed to be very strongly coupled at 5 days lag, when the observation expects you should be much less strongly coupled. And because of this, so this is as we ENSO monsoon coupling also faces this problem that since it is a too strongly coupled, then sometimes the error. So the one way to improve is reduce this strong coupling. And in the morning, in the as director IITM has suggested that it has improved because improved in the synoptic scale variability. Probably in this scale, we also have to improve the synoptic scales, or we have to improve the diurnal variability, because we know that there are a lot of drizzle bias in the diurnal variability in the CFS. And so probably improving the diurnal variability through this coupling, it will improve the moist static energy representation in the model, and this will help a better simulation. So this work is going on. Thank you.
Yeah, thank you very much. And I'm not so familiar with this MISO. And I was wondering, what's the typical? I mean, it sounds like a wave, right?
Yeah,
Sort of.
a sort of quasi-periodic wave.
And what is the frequency?
Frequency coming from approximately 20 to 80 days we take, or 30 to 60. So mostly it is 20 to 80 days.
So it's longer than the residence time of water.
Yes,
Yeah.
yes.
And I'm wondering, how does the variability look like? Does cloud cover change during that period? Or is it just rainfall?
Yeah, the cloud cover also significantly changes because see if you see convective cloud is very much strongly organized over this during the MISO evolution. So you have strong convective as well as stratiform component or the large scale precipitation. So this shows is quite spectacular evolutionary cycle as the oscillation moves northward during this up to the foothills of Himalaya.
And do you also have sunny periods in there?
Sorry?
Do you have also sunny periods?
Yes, sunny period is where the maximum rainfall is. Below that, there is a strong sunny, and north of that is also a sunny period. Okay.
Yes, so I wonder, how much do changes in solar radiation and heating that's ground by solar radiation play a role compared to changes in evaporation?
Yeah, so early theories, for example, there is a theory where say cloudiness has a role in controlling the scale selection, so temporal scale selection. So they said if you have strong cloudiness, you are cutting off the solar radiation, and then you are cooling the evaporation below the surface over the ocean, for example.
Yeah, and if you also reduce the
sensible heat fluxes. So that theory people explain, and they say that the scale selection of the subsystemnal scale is related to this feedback mechanism. So mostly that is shown over ocean, however. In land, for example, we are seeing the same thing because Webster already has shown that it has cut. Where it is raining, it is stabilizing it. The north of it, it is destabilizing it. So it is moving northward. So until the foothills of Himalaya.
Do you have a sense for how well this organization of prediction can be represented? I mean, I'm sure it has something to do with the grid resolution.
Yes, so like right now we are representing well in a 38-kilometer model. We can predict up to 2 weeks. So one way of saying that it is good representing. The other thing is the phase relationship between phase of rainfall with the vorticity, and all those things could be better represented in a 38-kilometer model. But higher resolution runs are also okay. But the intensity is not that much represented. So if you want to get the capture the rainfall intensity, so that's why I was telling dry bias. So whether that dry bias intensity is related to the soil moisture feedback, that is what we are trying to improve actually. Question? Question? Then thank you to with this, we end today's session.